Hi, I'm Matt, and today I'll be talking about our framework for high performance and accurate training data collection for self-driving database management systems. This work is part of the larger Noise Page project at the CMU Database Group. Before I present our framework, let's discuss the problem space for a moment. What is a self-driving DBMS? Why do we need training data? And why is collecting that data challenging? Database systems are ubiquitous in data-driven applications, but their increasing complexity makes them difficult to administrate. The goal, then, is to create a self-driving DBMS that automatically deploys actions to optimize its performance. These actions control all aspects of the DBMS's configuration and include physical design like adding and removing indexes, knob configurations related to the buffer pool, auto vacuum, and background writers, and hardware resources like instance size in a cloud deployment. A key component of a self-driving DBMS is its behavior models, which estimate the benefit of candidate actions. These models need to be accurate, which in turn means we need robust training data. In order to illustrate the structure of the training data, let's briefly look at how Noise Page uses a behavior model. In order to predict the resource consumption for a SQL query, we first generate input features to describe that operation. For a sequential scan, this includes operator-specific information like the execution mode, optimizer stats, and filter expression complexity. Given these inputs, the behavior model outputs low-level metrics of the system resources consumed by the DBMS to execute a query. These metrics include detailed CPU counters like cycles, instructions, and cache references, as well as I/O measurements like disk and network. These two vectors of input features and output metrics are the training data we want to collect. Next, we need to talk about where training data comes from, and we'll approach that in two parts. First, we'll look at the input features, which describe the work being performed. The first approach observes the DBMS externally. By invoking extra queries and scraping DBMS state, it's possible to extract descriptors for use as input features. However, this approach is difficult in high-performance scenarios and doesn't expose interactions of queries with background tasks. The second approach uses knowledge of the DBMS internals and requires source code modification to collect state. This internal state yields richer features and thus simpler models requiring less training data. Next, let's talk about the outputs of the models and how we collect metrics. For collecting resource consumption like CPU and disk, the OS provides APIs to observe system behavior. We used this user space approach in our previous work. It's safe, it's easy, but it incurs significant overhead. Depending on how much data you want, it requires multiple round trips from user mode to kernel mode due to syscalls, and you're limited in what the OS exposes to you. An alternative would be to look under the hood and monitor the resource behavior within the OS. This approach is similar to the internal feature collection approach we just discussed. Running in kernel space offers better performance, but it's potentially dangerous. In the past, this would require writing a dedicated kernel module. Enter BPF. Originally a way to perform packet processing, since 2014, it's a general observability platform in the Linux kernel. You'll hear some people call it eBPF, but we're sticking with BPF today. It's a virtual machine that runs inside the kernel, providing access to memory and functions that can't be read from user space. BPF is safer than kernel modules due to the verifier that all BPF programs must pass. But that verifier comes with a price. BPF programs need to be short, bounded, and access memory safely. In return, you get access to kernel data structures about the process, like its task struct. These things describe file descriptor tables and kernel statistics about scheduling. There are also countless hooks throughout the kernel to observe operations that are difficult to measure externally, like the OS page cache. In addition to the extra information you get from kernel metrics, BPF saves round trips on syscalls. One transition to kernel mode, and the BPF program can collect all the information it needs. To show this benefit, we ran TPCC with no metrics, user space metrics, and kernel space metrics. These metrics include CPU perf counters, network, and disk consumption. The chart shows the P99 latency of the workload, which we chose because the syscalls of user space execution are prone to CPU scheduling stalls, thus resulting in higher tail latency. The takeaway is that kernel space metrics provide better performance to collect the same data. While the absolute differences seem small, the frequency at which these events occur makes every difference count. Let's recap how we'd like to collect our training data. We want DBMS internal features for its detailed information about the entire system. We want kernel space metrics for their low overhead and similarly rich information about the OS. And a major benefit of low overhead collection is that it allows us to get training data in an online setting. This training data better represents target workloads, and we can adapt our models to changing hardware without adding too many input features. With that wish list in mind, we designed Tscout, a framework that takes an internal approach to DBMS feature extraction, along with kernel-level metrics collection to generate training data for self-driving DBMSs. To describe Tscout, I'm going to incrementally build this figure by adding things in the order that they occur. Describing programs running in user space and kernel space can be tricky. Tscout starts with the notion of probes, which are simply a piece of code that measures a resource. Tscout includes probes for kernel metrics like CPU, disk, and network. Memory is a user-level probe because it's already tracked for knob configurations, and most DBMSs implement a custom allocator with metrics. A kernel-level memory probe also doesn't make sense because virtual memory makes it hard to track allocations, and tracing every malloc call is infeasible. Starting with the DBMS source code, the developer defines user-level probes along with boundary markers for measured operations. For example, for sequential scan, a begin marker is added at the start of the scan, along with corresponding end and features markers. At startup, Tscout inspects the source code annotations and any user-defined probes and generates a BPF program called the collector. The collector includes logic for kernel-level probes, feature extraction, and temporary data storage called BPF maps. Tscout JIT compiles the collector and loads it into kernel space. There, the collector waits for an invocation by the DBMS running in user space. Upon query arrival, the DBMS creates a plan and starts executing the scan code. After traversing the begin marker, execution transitions to the collector, which uses the probes to read metrics and stores the intermediate results in BPF maps. The sequential scan continues until completion, whereupon the end marker invokes the collector again, which stores final metrics in the maps. Finally, upon traversing the features marker, the collector aggregates the input features and output metrics into a buffer and sends the training data to a user space processor. There, the processor transforms and archives the training data to the desired format. Let's briefly discuss Tscout's overhead and performance. To show the overhead of training data collection, we run YCSB over JDBC for 60 seconds. Then, we enable Tscout for all components at 10% query sampling. After another 60 seconds, we disable training data collection for the execution engine as if we've got enough training data on that component. But we keep collecting training data for other DBMS components like network layer and write-ahead log. Tscout incurs about a 7% drop in performance while collecting training data. When Tscout is enabled, throughput of training data generation is about 30,000 examples per second. For the execution engine alone, this process yields nearly 2 million training data points. While this isn't a modeling paper, I do want to briefly point out the benefit of training with online data, particularly after a hardware upgrade. This scenario runs CH benchmark on a server trying to predict execution engine performance. Noise page starts with models trained on a weaker machine from offline synthetic training data. The y-axis here is a measurement of model error, and we'd like it to be as low as possible. The models trained on offline data is our baseline. When we enable online training data collection and refine our models, we see that supplementing with online data always does better. It doesn't take a lot of training data to improve, but not all quantities are a strict improvement over others. I think there's a lot of interesting future work in exploring when to refine models, how much data to collect, and what online training data is most valuable. Let's summarize by revisiting the wish list I described earlier. We wanted DBMS internal features, which Tscout provides via source code annotations and a shared address space with the DBMS. We wanted kernel space metrics, which Tscout's collector supports via BPF. Tscout's processor moves training data archiving off of the critical path. Lastly, we wanted a framework for online data collection, which Tscout enables with low overhead and adjustable sampling. Thank you for listening. If you have more interest in Tscout, I encourage you to read the full paper for more details. I'm excited to explore more ways to marry the DBMS and OS internals with tools like BPF. I'm happy to answer questions now.